every semester in the past that okay, good. That is like that that the tests were up here, and I put them out here this morning, and I trust that most of you have gotten them, and then we will kind of, if you want to slide this over a little bit, feel more than free, so that you guys can have some place to work here again. I'm going to put that in the middle there, just for a few more minutes. Why people come in and get it. But let's take a few minutes to go over the exam and see the point. You can see that, at least I hope, that some of them were kind of easy and straightforward, and others of them were not easy at all, and really involved particularly the hemisphere of getting that electric field in the center, and that was definitely a challenge one. I suppose the first thing you should do before you even look at your score is kind of lift up your right hand, put it over your left shoulder, pat yourself on the back, and realize that I think, it's debatable, but I think this is the hardest set of topics we have done in all of the three sequences, whether Physics 121, 122, and 123. And I know that's kind of debatable because we did some hard stuff in 123 in the thermodynamics. I knew we did some hard stuff with the rotations in 121, that's for sure. But this class started off really, really hard, and now we have a fairly set of simple chapters, at least for a little bit. Then we get into magnetism, and it maybe gets just as hard again here. So it'll come back as we get into magnetism. That's for sure. But I know that this is the one that I usually say. I don't know if I said it this springtime or not, but I always comment how it's always a rude awakening for students when they come back in late August and hit chapter 23, because 23, 24 were some brutal chapters. Anyways, you're done with the test, good. And actually, I'm done grading it, good, because this is always a real hard one to grade. There are so many different directions people can go, and so many different wrong answers that they can create. And especially if it's at the very beginning, because, you know, the whole thing looks wrong, but there's times where the whole thing is wrong, and there's times where only part of it is wrong, and there's times only just one thing at the very beginning is wrong. And so I did my very best to try to notice that and give you points accordingly to not just what was the answer, but how bad or good was the logic along the way there. And so let's run through this. I'll start with the first one. It's got three parts to it, A, B, and C. Hopefully A and B were pretty straightforward for you. It's an exact copy of what I did in class. And so if you missed it, let's look at A and B. Now C, if you got C, good. You were thinking, because that was something totally new here. But number one, A, is simply saying this. Go ahead and start with Gauss's law. Given the ball has a uniform charge, given the ball has a radius of capital R, total charge Q, write or derive the electric field when you're inside the ball. So hopefully you started here. This is kind of what I was looking for first. This is Gauss's law. And so obviously this was straight from chapter 24 here at the very beginning. Gauss's law was one of our three techniques that we had to find the electric field. And as we think about a ball of radius capital R, and we draw a Gaussian surface of radius, say, little r, then this becomes the electric field times 4 pi r squared. After we first did the dot product, then we argued by symmetry, the angle would be 0. Then we can factor out the E, we argued by symmetry, and then got the surface integral, and that's where the 4 pi r came from. Then we have the charge inside over epsilon naught. The charge inside is probably the part that makes it a little bit tricky here. Maybe we should call this rho for the density times the volume that is inside. And so if anything's kind of hard to remember, it's what R are we using? And so this is the R of the Gaussian surface. And in this case, this would be the little r also would be the R of the Gaussian surface, because we're looking at the charge inside of the Gaussian surface. If we take one more step here and say the density would be the whole charge divided by the whole volume. And so in that case, I would use a capital R, because again, it's the whole volume. And so a couple things cancel out. Obviously the 3/4, obviously the pi, being left with E on this side. I can put the 1 over 4 pi epsilon by itself. There's the 4 pi, there's the epsilon. I can put the Q. It looks like 2 of these R's cancel with 2, leaving just 1, and then an R cubed. And so there would be the electric field on the inside. And again, I did that for you, and I know the book did that for you, and it's, again, kind of your classical Gauss's law. How do you use it? B, I think, is even a little bit easier. Again, it starts with Gauss's law, but now it says outside. And what makes it a little bit easier is when you're on the outside, the charge inside your Gaussian surface is the total charge on the ball, no matter how far you are on the outside. And so the electric field reduces down to 1 over 4 pi epsilon naught, and then we've got Q over R squared. And so one thing we mentioned and talked about in class was that when you're outside the ball, it's the same as a point charge. And so sure enough, we got the same equation for a point charge. Now the C is a little bit new here, and it's going to make you kind of think around here. It says here, what if you had a non-uniform charge density? And the question asks, what would that uniform charge density have to be in order for the field to be radially outward and a constant value? So starting with Gauss's law, again, and doing a Gaussian surface on the inside of the ball here, this left-hand side would still be the same. It's the right-hand side that's going to make you think a little bit here. How do you get the charge inside the ball? Especially if inside the ball is not uniform. Well, probably the best way to think about it first is to say, well, I could add up a bunch of chunks of charge. Okay? Now, to be radially uniform, we needed that statement right back here in Gauss's law. The only way we can take the dot product and pull it out, which I did kind of quickly here today. In fact, I guess I'm doing all of this kind of quickly. But as we argued in class in the lecture part of this, that if it is radial symmetrically, then you can pull it out. But if I'm going to pull it out here, I need to know something about the charge distribution. And that means the charge distribution has to be a function maybe of R only. In other words, no matter where I move from the center of this ball. So if, again, as I was in class, I like to kind of use this as my reference point. But if this is the center of the ball, if I moved out to here to have the same electric field here as over here, the charges around me would have to look the same. I'll simply put then, what I'm really saying is that if I write this as charge density times volume, so in other words, charge density is some function, then this number here has to be some R raised to some power, right? It has to be a function of R. What function of R, I don't know yet, but that's the whole idea of the problem. So I'm going to write this as some constant C times R to the n, and then I will write my volume as 4 pi R squared dr. Again, those are adding volumes that are in the shape of shells. And we could do some more work here, but maybe you already see it. In fact, maybe you see it back here if I had just written it as rho times 4 pi R squared dr with an integral. I think the hardest part of C is the realization of this. If E is going to be a constant number, that means when it's all said and done, there should be no R's left. Fair enough? And once you realize that, then it's pretty easy. No R's left mean that there's 2 of them on this side. So you better get how many? You better get 2 on this side. Now remember, we're doing an integral, so that's going to raise it by a power of 1. So that would be perfect if that had a 1 over R type of value. The 1 over R would then cancel with 1 up here, leaving you with an R. Then when you integrate it, you would get an R squared. And the R squared on one side would cancel with the R squared on the other side, and you'd be left with something with no R's in it. That was the real key. If I keep going this direction that I started to do a moment ago, and just say it's going to be R raised to some power, you can see that when I do this integral right here, I get R, and that's n plus 2. So when I go n, when I do an integral, I'm going to get n plus 3. Of course, I'm going to divide by n plus 3. Then I'm going to have the rest of all that gobbledygook in there. But again, the realization here is, if this is what I have on one side of the equation, and on the other side of the equation I have R squared, those have to be to the same power. They have to cancel off if you want to get E equaling something but has no R's left in it. And so that tells me that n plus 3 must be equal to 2, or simply put, n equals a negative 1. And so that answers my question. And so that would have to be the way the charge is distributed. And so, again, for those of you who did see it while you were working the test, that was that kind of that magical enlightening moment, if you will, of like, okay, what am I looking for? E to be a constant means there's no R's left. That's the real key there. So that was a tough one. So if you got that one, congratulations. If not, when I turn the page, let's move on. All right. Let's do this next one, number 2. Number 2, I'm hoping you see it's exactly what I did in class, except an added switch. The problem I did in class had 2 switches. This one I just added a third switch on there. And so the problem looks, of course, something like this. You have a voltage supply V, and then you have your first capacitor C1 with a switch. Your second capacitor, this is kind of dry also. Is this one any better? A little darker. Your second capacitor has another switch, S2. And your third capacitor has a switch S3. And so, again, what they say to do is first just close switch number 1. Well, I would call that step number 1. Since the capacitance then of number 1 would be the charge that builds up on number 1 divided by the voltage V, since that's all that would happen, my first step is to say, okay, capacitor number 1 now has a bunch of charge. Well, how much charge? Well, it's hard for me to write this number down because depending on what test you have some different numbers. But those of you who have the white test, if you look at C1, it's a 10 microfarads. And the voltage is 9 volts. And so that gives you 90 microcoulombs for the first charge. I guess if you have the green sheet, so this will be white. If you got the green sheet, that comes out to be 1200 microcoulombs. If you got the gold one, it comes out to be 900 microcoulombs. All right. But that's logic number one, is just, okay, how much do we originally put on? Now the problem starts to get a little hard, because what we're going to do is open switch number one, which means then that charge cannot go back to the battery. And that's the key to the understanding. That's when I did this one said, opening that switch is really the key, because now what remains constant is the total charge. Because after I open switch 1 but then close switch 2, what's going to happen is some of the charge on number 1 will come off and flow to number 2. Now it can't go to number 3 at this point because that's still open. But there'll be a redistribution of those charges. You might label it this way, that Q1 and now Q2, and I'll put a little prime so that we don't confuse Q1 with what I originally did here. Because this is the original, at least 90 on the white one. That is going to flow off, and so this is going to go down. Of course, this is going to go up. But what remains the same is the 90. Or the 1200 or the 900, depending on what test you have. But that is a big understanding of the problem. Also, the other big understanding here is, well, how much flows off of here? Does it all flow off? Half of it? I mean, what is the condition required for this to stop flowing and the new balance is achieved? Yeah, when they have the same voltage. So you might write the voltage on number 1 is the same as voltage on number 2, which we can calculate voltage by saying the charge that is now on number 1 divided by its capacitance, and the charge that is on number 2 divided by its capacitance. That has to be. And so that's perfect. There's 2 equations and 2 unknowns. That right there will allow us to solve for charge number 2. And so if you have and I thought I'd do the white sheet first and then move along, but if you've got the white sheet, then your first capacitor is a 10, as we did over there, and your second capacitor is a 20, which means that 2 times the charge on number 1 is equal to the charge on number 2. Okay? Knowing that, we can put this together, and you are going to get 3 times the charge on number 1 is a 90, which means the new charge on number 1 is a 30, which means the charge on number 2 is the 60. And so the second step is to realize how much charge ends up on number 2. It's a 60, at least for the white sheet. If you do that same kind of logic for the green, it comes out to be 800. Your numbers are a little different, and your ratios are a little different. If we do that for the gold sheet, then it looks like it comes out to be a 300. And so, little slight different numbers there. And then we just got to do this one more time. Okay? And we're going to close that switch again. But for those of you who might have missed a few points, catch the physics of it. It is not that all 90 will come off, as some of you indicated by your calculations. I don't know if you meant for your calculations to indicate it, but you just said, oh, 90 goes to here, 90 goes to here, 90 goes to here, done. No, or some of you just cut the voltage in half. Well, if it was 9 here, then it must go 4.5 here and must go 2.25. No, that's not what would happen. What will happen is it will flow till the voltages are equal. Whether that be halfway or not, all depends on the ratio of the capacitance. But what is got to be the same is the conservation of charge. The total charge doesn't change. So I would call this kind of a step 2 in the problem. And so now off to step 3. and say, all right, what's going to happen? And it's going to be very similar. Now that we have 60, and we go ahead and we open switch number 2, and then close switch number 3. That opening of switch number 2 means no more charge can go back, either to the battery or charge our capacitor number 1. And so when it flows from number 2 and then goes on to number 3, what'll have to be the same is our conservation of charge. And so that's got to be our 60. And if it helps, I put a double prime here to kind of indicate, okay, this is the third time here. What is my charge after all that takes place? Just to make sure I realize that, okay, charge on number 2 was 60, and now I'm going to do something with it, so the charge is going to change. But again, what would happen is charges would flow around, not till the voltage is cut in half, not till all the charge goes off onto the other, but when those two voltages are equal. And that's the key step in physics. I like to call this conservation of charge, conservation of energy, right? That's probably not a bad way, that's probably not a good way of saying it. But in this case, this is the forces, pressure, if you will, are balanced. They keep flowing until the push, the electric field is the same push there. But then I can do this same type of mathematics. That Q number 2 double primed over capacitance number 2, and Q double primed over 3, over capacitance number 3, those would have to be equal. And so if you put in your numbers, which for the white sheet was a 20 there and a 30 there, you finally come out with the charge on number 3. And so the charge on number 3 comes out to be a 36 for the white sheet. Doing that same arithmetic for the green one, it's 480. And doing it for the gold sheet, 225 microcoulombs. And so, again, hopefully you kind of caught all that. Going to the next one, and maybe the next one I'll use the numbers off of the green sheet here. But as we look at number 3, the problem is something like this. You have a negative charge on a hemisphere. Ah, that's something new. And then we start with an electron that is placed at the center of that hemisphere. And of course, because it's negative, it pushes it away. And we also have another hemisphere. It's a positive charge. So not only is it pushed away because of this one, it is attracted over because that one is positive. And so this electron is going to move, and it's probably going to be going pretty fast by the time it gets to that other hemisphere. Of course, it depends on how much charge it has. But they don't have much mass, so these things move pretty quickly. And so what I was looking for first was realizing this is a conservation of energy problem. This is, in that little diagram we did when we got started in chapter 25, is if you know the potential and then the charge, from that you can get energy. And that's the key to this here. So I would start off by saying over here would be the electron times the voltage I have initially. You might even say plus 0 kinetic energy, so that you realize you're adding up all the energies. And then I would say it moves, and now it's at another potential. So it'd be the charge of the electron times this new potential. plus any kinetic energy it has. And so there's the magical step right there, right? That is it. Find this speed. And that's kind of the first half of the problem. The other half of the problem is saying, well, wait a minute, I've got to know the potential. And the potential is created by all these charges that are in a hemisphere. So now you're going to have to kind of stop and say, ooh, how do I get the potential from a hemisphere? We didn't do that one in class, and we didn't have that one in the book. Fortunately, it's pretty easy. The potential can always be thought of as the sum of a bunch of charges given their distance away. So this is what we call a little dV, right? This is the potential from one single charge. And so if we add up all the charges, we're in good position for it. And so if you kind of look at all these charges that are on this hemisphere, and say, okay, those charges are what distance away from this point where I would like to eventually put that electron? Well, you can see why I picked a hemisphere. It's going to make the math pretty easy. They're all the same distance away. It's the radius of it. So I'll just call it the radius of the ball and pull it out. And there's Coulomb's constant. And so then we just get a dq. And so the equation for the potential in our hemisphere is kind of a simple formula. It's just Coulomb's constant times the charge on the hemisphere times the radius of it. They're all the same distance away there. And so that's going to be our potential. It looked like a number of you tried to do the other option, which is to integrate the electric field. And of course, that was another way we had. In fact, it was the idea that started here, which led to here. And so we did some problems like this, and we did some problems like this. I think you can see that this is the way to do this problem. This one, I'm not sure. Well, it's got to be solvable because I know this is it. So I was about to say, I don't know if you can solve it, but I guess you should be able to because we know it comes out to this. Or maybe I should say, I'm not sure you could do it in 2 hours. How's that? Because you would need to know the electric field, not just at the center of the ball, which, by the way, is question 5. And so some of you realized, oh wait, maybe this is tied with question 5. Well, not really, because question 5 found the electric field only at the center of the ball. What would you need to know is you would need to know the electric field at every point so you could integrate from the center of the ball to infinity. And so you would have to integrate from the center to infinity, or the other way around, infinity to the center of the ball. And so I'm not saying it can't be done, because like I said, it must come out to be here. But finding the electric field some distance x from the center of the ball does not seem like an easy proposition. I gave you the easy one. It may not have felt like it on problem 5, but I said find it at the center of the ball, because there's nice things about the center of the ball. All the charges are the same distance away. But if you had to find it at some random distance, then each of those charges that make up rings on this ball would be really, really hard. So, not a bad first thought, but after 10 minutes, stop on that. That's getting you nowhere. Jump to this. This is the way to go. Real easy way to get the potential. So again, this is the idea, and put these two together. What's the potential from a hemisphere? And then use it with our conservation of energy. So when I do that, I can take the charge of the electron, and I'll just put it in symbols first, and then I have to give you the potential. Now the potential from a hemisphere would be K times that negative Q1 divided by R. And I suppose if you want to be complete, I should say 0, because remember, the potential is created by all the charges around it. So I would have the potential created from this hemisphere plus the potential created from that hemisphere. But you'll know I deliberately said, think of these as being very far apart. What does this actually say? Yeah. if the two hemispheres are very far apart. And that was the purpose for that wording, was to say, look, we easily calculated the potential at the center. That was this one. But if you've got to include the potential of that hemisphere, when you're not at its center, that's not what I was asking you to do in the short time you had to take the task. Again, I think it probably could be done, just like finding the electric field off of the center could probably be done, but probably not within a 2-hour time frame. So hopefully you noticed that there was really no additional potential you needed to include from that other one. It was far away. That was the idea of there. And the same thing in reverse over here. If you take the charge of the electron and then you multiply it by the potential that is created by this hemisphere, and then I guess technically 0, because remember the potential would be not only the potential created by the charge on this hemisphere, but also that hemisphere. But again, really far away. So I'll put a 0 there. And then you get your 1/2 mv squared. And then it just falls into place. We know the charge on the electron is a negative 1.602 times 10 to the minus 19 coulombs. At least I hope I gave that to you. Ah, good. Negative, this is 9 times 10 to the 9th for Coulomb's constant. The charge, now of course, depends on what test you have. I think I've got the green one here. So the green one had a charge of negative 10 nanocoulombs and a radius of 12. Over here we'd have a negative 1.602 times 10 to the minus 19 coulombs. We would have Coulomb's constant again. We would have the charge on the positive one, which in this case is 15 nanocoulombs. And it did say it was an identical hemisphere, so it would be the same radius. Oh, sorry about that. And so that would be the final energy. So initial potential energy, final. Again, notice a negative number, notice a positive number, so they're going to build together when I move it to the other side of the equation. 1/2, and I'm sorry about this, I'm glad Don gave it to you, but I guess I forgot to put the mass of the electron on there. Don tells me many of you remembered it good. That was, right, 9/11. October 31st, right? And so we've got our negative events for the fall there that we'll put there. So 9/11, October 31, with the negative, all the negative events in fall with the negative charge. But after a little bit now of arithmetic, we should get the velocity. And again, I'm doing the green sheet. So on the green sheet, I got 2.57 times 10 to the 7th meters per second. So really fast. Not quite a tenth of the speed of light, which those of you who've done Physics 123 will know. We need to be careful. Some things change that you learned when we get close to the speed of light. And our definition of close is about 10%. So didn't quite get there, so that's good. This one, the white one, had some slightly different numbers. In fact, numbers that were maybe a hair too high, because this one actually did kind of go above 10% the speed of light, but not worrying about what we will call relativistic effects. I'm just going to leave it as that speed. And then the gold one, the numbers are a little bit less, so we get a little bit lower speed here. And you should have got 8.89 times 10 to the 6th for the speed there for the gold one. Yeah.
Why is there the negative in front of KE?
Oh, the, sorry, I did the negative twice. Shouldn't be, it should be negative the absolute value. So negative the absolute value, yeah. So that negative and negative is positive, good, yeah. And then that one should be negative, good, yeah, yeah. No, so there should not be. All right, let's go to number 4. And again, hopefully number 4 looks exactly like what we were doing in class. We hooked up a bunch of capacitors and looked at some circuits that were equivalent. And that equivalency made it possible to simplify the circuit so that hopefully we could find the, in this case they asked for the charges and the voltage. I think in class I did charge, voltage, and energy. I didn't ask energy here on the test. I thought that would be enough and didn't want to take too much time so you'd have time to do the other parts here. But I did warn you, and notice this when you guys started working on it, that one of the hardest things to connect right away is whether or not your capacitors are in series or in parallel. Because as we argued here, that when they are in series or parallel, that's a different flow option for those electrons. And that different flow options mean different things happen, which is why we got different equations on how to handle the equivalency when they are in series and in parallel. So the toughest part, I think, at the beginning here is to notice when a circuit is in series or in parallel. And 3 and 4 can be a little tricky here. That was this whole idea. Are 3 and 4 in series or are they in parallel? Series. Yeah, and I hope you see it's in series. Series meant that as, say, negatives came off of here and piled up onto, say, C4 and chased an electron off and went to here, series meant exactly that. It had no other place to go but that next capacitor. And we're going to see the same thing as we get started with our next unit on resistors. We're going to ask them, are they in series? Are they in parallel? We're going to play the same game here. And in this case, they are in series. So what I like to do when I do a problem like this is to redraw it, leaving C1 and C2 alone, and then replace the 3 and 4 with what it is equivalent to. And since they're in series then, if you take 1 over C3 and add it to 1 over C4, so the reciprocals, you add them, and then you take the reciprocal of that, you will get the equivalent. And as I tried to point out, I like the reciprocal key on my calculator because by hitting it 3 times, you can make short work of this. And so if I use the gold one, C3 is a 25, so 25 reciprocal. C4 is a 60, so 60 reciprocal. Add them together, hit reciprocal, hit enter, and this comes out to be about a 17.6, at least for, what I say, gold here? On the gold sheet, microfarad. And so that's my first equivalent circuit. Then I like to draw it again and say, anything else do you notice? Well, hopefully you notice that this 17 is then in parallel. Remember, parallel means that the electrons that come off can go here or they can flow on to there. And then the electrons that come off regroup and go that way. So this side are connected and this side is connected with a wire. So therefore they're in parallel. They have the same voltage on them. And so we handle those differently. So again, maybe a big step is noticing that you can put those two together and that they are in parallel. And so you get an equivalent of 47.6. because here you're just going to add the 17.6 together with capacitor number 2, which is a 30 for the gold sheet. And then the last one to draw is to say, what is this all equivalent to? Well, again, hopefully you notice that in this picture, those are in series. So the 47 reciprocated, going with number 1, which is the 15 reciprocated for the, again, the gold sheet there. But you will come out with then 11.1 microfarads for, again, the gold sheet. Now, as I was trying to say, and I really am going to emphasize it as we get into resistors, these are great, but they're only equivalent. This is not the real circuit. This is not the real circuit. This is not the real circuit. This is the real circuit. And so these are only helpful in the sense that they let me solve this one. And so certain parts of them are useful, other parts are not so useful. But I would claim this first part right here is very useful, because if I actually had a circuit that looked like this, then this voltage times the equivalent capacitance would tell me how much charge goes on that capacitor. Now, the reason that is helpful is because if I look back at the real thing, you would see that that charge comes off of here and flows into here. And so whatever charge I get here on this equivalent one is the charge on capacitor number 1. And so that's the first and important step here. And so filling in this chart here that says, hey, what is the, uh-oh, I lost my gold one. Wait. Green. Gold. I should have put colored paper in the printer too. But looking at this one in your table, they say, what's the voltage? What's the charge? If you put in your voltage of 5 volts and the equivalent of the 11.4, you're going to get a 57.04 for the this one, the gold one, yeah.
Okay, so you got the 47.6 from the voltage of the C equivalent?
Of the, right. Right. So C2, which is a 30, and this equivalent one are in parallel, so I added them together to get the 47. Yeah. And so again, what's nice about this equivalent circuit is it lets me find this equivalent circuit. And so again, each of these circuits are equivalent, so we can use each of those to help us answer this question, what's going on with this circuit? And that's why I said it does. This equivalent one does help us already, because that would tell me how much charge comes out of that battery and how much goes in. And the stuff that comes in is coming from capacitor number 1 only, so that's why this one is the answer to capacitor number 1. How much charge is on number 1? Unfortunately, that would not be the charge on 2 or 4 because it splits off here. So I still don't know how much is on 2 and 4. All right. But it is a little bit helpful, at least it gets me started, because again, the capacitance here is a 15. And if you know any 2 of these, you can always find the third. And so remember that capacitance is charge divided by voltage here. So to get voltage, I could take this charge and divide it by that capacitance. And when I do that, I get about a 3.8. I wrote a few more decimal places just to help me with my rounding. But I got 3.803. Now, why is that helpful? Because if we continue on down here, we can take that information and do a couple things with it. The first one is to realize back here on this equivalent, we have just figured out that that is 3.8. Fair enough? This is 5. What does that tell me about the voltage here? Right, that's got to be the 5 minus the 3.8. These two are in series, and we took two capacitors in series. What happens is an electric field will build up until the push of these two together equal the push of the battery, 5. And so that comes out to be about a 1.2. So what's nice is it tells me that that's a 1.2. Now again, how does that help me with the real circuit? Well, if you look at that capacitor is equivalent of these two. These two are in parallel, but that's the same voltage, and that is the C2. So my next line would be, hey, I know that right there. And I can get 1.2, actually 1.97 if you kind of round what I have there. And as long as you're here, you know that you have two of them now. And so you can find the third. And so this comes out to be about a 35.91 there. And so we know how much charge is on here. And actually, I'm sorry, on here. And that's where it becomes real helpful again, because if that charge is 35.91, and we know the charge on this guy is 5704, then the fact that this one has more charge is because than this one is because some charge came from here, but some charge came from there. So isn't the difference really the charge coming from there? And so if I subtract those two, which gives me a 21.13, that would be the charge there. Now again, of course, this is not the real circuit. The real circuit is here. So if this is helpful in any way, then I'm glad I did it. If it's not helpful, well, then maybe something else will be helpful along the way. But notice I'm looking at this equivalent one, and this equivalent one, and this equivalent one. And I claim that this is very helpful. This is the charge on that equivalent capacitance, which, as you look at these guys, you're putting them together. That is the charge on one of those, right? And so that's I guess the whole point is to say, okay, this charge came from this going over in that direction. So that's what this is saying. The 21 went over there. So the 21 must have went to C4. So C4 must be the 21.13. And 21.13 must be C3, because whatever charge then came over onto C4 continued on up to C3. And so again, take your equivalents and look at each of your equivalent. Each one is a little simpler going that way, a little more complex going this way, and so each step moving back to here will allow you to find your unknowns. And in this case, once you have your charge together with your capacitance, 2560, you should be able to find the third one, because of here. Okay? And so just a couple of steps backwards. And of course, that is all for the gold. If I write this out for the white, this is a 7.092, 1.908, 1.092.819. This then becomes a 7092, This becomes a 3.816. This becomes a 3.276 and 3.276. This is units of microcoulomb and this is units of volts. The green one would have these numbers: 15, 1, 4, 8, 6, 2, 7, 0, 2, 1, 6, 30.2, 19, 42, 10, 72, 78, and 10, 78. Okay, and so try that logic if you had one of these other ones, but same logic, obviously different numbers here in terms of what it comes out to be. All right, and finally, number 5, the grand finale here, has 2 parts, purposely. I think the part B is a hard one. It was deliberately giving you something new, something you haven't seen before, so that you would think through it. But the first one on was exactly the flip of that. It was what is it for a ring? We did a ring. I think it was the first one we did back in chapter 23. We got started and said, all right, what is the electric field from a ring? You started with the idea of what is the electric field from a point charge. So let me start there. If I had a small amount of charge, call it Q, I would get an electric field of Coulomb's constant times Q over R squared. Maybe to write it in a differential form, I could say a little bit of charge would create a little bit of electric field, and it would look something like that. So a little bit of charge gives me a little bit of electric field. Perfect. Okay? But now if I have a ring of charge, and I move out some distance x, where then the ring has radius of capital R, then a little chunk of charge up here, dq, would create a little electric field, which is equal to Coulomb's constant dq over R squared. Now, the first step in this is to realize that there would be another little charge down there that would be pointing up at that angle, and the vertical components would cancel off, and so you're not going to get any vertical components. So you could say then that the electric field in the y direction is going to come out to be 0 from symmetry, and just leave it at that. But the electric field in the x direction does not cancel off. The electric field in the x direction has to be the summation of the electric field in the x direction for each of these. So breaking this vector down, calling this the angle theta, we would have the magnitude of the electric field times cosine of theta. And the magnitude of the electric field is Coulomb's constant times Q over R squared cosine theta. And so that's kind of our first couple of steps, is just, okay, what is the electric field from a point charge? Then we want a component of it. That's where the times cosine theta comes into play. Fortunately, a couple of things remain a constant in here and can be pulled out in front. For example, Coulomb's constant. Doesn't change. Interesting enough, as you draw this line here, because it's a ring, all the charges are the same distance away. So R squared doesn't change. In fact, let's write it this way. This would be R. So if we use Pythagorean's theorem, this becomes an x squared plus an R squared. And that doesn't change, and so I can pull that out in front. Also, for that matter, the angle theta doesn't change. It's what made this an easy calculation. As you go around, you can add up all these chunks of charge. There's no changing in the angle. So the only thing you're left with is an integral of dq, which is another reason why it becomes easy. I mean, what does that give you? Well, that's just the total charge. So that's just Coulomb's constant, x squared r squared, cosine theta, and then that's just capital Q, as we were add up all the chunks of charge. So there's no really distance or angle to worry about. This one's pretty easy. Okay? To make it look like the form you're familiar with in class, let's do another substitution. Cosine theta, then, as you look at this angle theta, it would be the same as that angle theta. It would be the adjacent, so that's an x, over the hypotenuse. Well, that would be an x squared plus an r squared to the 1/2. And so putting it all together, we get an x squared plus r squared to the 3/2 power down on the bottom, and then an x and a charge and a Coulomb's constant up on the top. And so that was our equation for the ring that, again, your author did for you, I did for you in class. I think you even had homework to work it out too on that one. And so that, I hope, went well for you. Now, how'd you do here? And if you didn't get this one, don't feel so bad. Many of you got really close, and I think you should be proud you got really close. And actually, many of you even got it completely right, and I was kind of impressed with that. But now we need to add up some rings. And fortunately, it comes out to be really simple, but it may not look that way for a while here. So let's work through this here. Let me put a hemisphere up here. Let me place my point of interest right in the center of that hemisphere. I tried to help you out by giving you two hints. The first one says, think of this as a sum of a bunch of rings. You see, we already know the electric field from a ring. Now that's really nice, because from the ring, if you think about what we already got from the ring is already telling us that we only have an electric field in the x direction, and the electric field in the y direction is 0. And so as we go to figure out what the electric field is at that point, it's going to be a bunch of x components added together. Nothing's nicer than adding vectors that are all in the same direction. And so that's a nice first step by saying E for this hemisphere is going to be E in the x direction only. There's not going to be a y component or a z component. There's no way you can take and add a bunch of x's together and get something that's in the y. So all the y's are 0, and so that's kind of the first step, is to realize, okay, they're only pointing in the x direction. And so a little diagram would say a little plus 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 a little, right? And so all in the x direction. And so what I need to do then is add the electric field in the x direction from a bunch of rings. So there's the hint, or at least there's the hint written in mathematical forms. Verbal form, it said just add up a bunch of rings, okay? And so now I can take this result and say, okay, I'm going to add up a bunch of microscopic rings. Here's probably the hardest part of any of these integrals we've done, whether they be the integrals we did for getting electric field back in chapter 23, or whether they be the potentials that we got over here. You're adding up some little tiny something, right? So you have to have a d something over here. What? D what? And this is a big step. Yeah, and those of you who are brave enough to mention it obviously saw it. What we're doing is we are making a ring here that is really thin. So here's my ring. And as I look carefully at this equation, what is getting small? Is it x? Is it r? Is it q? It is not x, right? What is x? Yeah, x is the distance from the point I'm interested to the center of the ring. So in my diagram, that would be x. And as I am taking thinner and thinner and thinner rings, does x go to 0? No. So it doesn't, dx does not go here. Does dr go there? Well, what's r here? R is the radius of the ring. So again, as you are thinking of this ring as being cut thinner and thinner and thinner and thinner, is r going to 0? No, not for one particular ring. Now granted, there are rings back here that would have small radii. But for this particular ring that we're cutting thinner and thinner and thinner, we're not letting the radius of the ring go to 0. So it's neither of these that go to 0. What is going to 0 is the charge on the ring, because you're cutting the ring thinner and thinner and thinner and thinner. So there is a big and important first step when you go to apply your physics and integrate that with your calculus. Integrate, no. But when you go to do an integral, you do have to figure out what is the object that is getting smaller and smaller. So I emphasized it before. I did it in 121 when we did center of mass. I emphasized it here when we did chapter 23. Emphasized it again when we did chapter 25. Hopefully you picked it up. I'm taking one last shot at it because you know what? You're going to see it again. We're going to get to magnetism real soon. And we got to realize, how do you get the total magnetic field? Add it all up. Exactly. And we're going to do exactly the same thing in the second half of this class here. So catch this now before we go too much further here. But that would be the first, I think, big step here. Then it still gets kind of hard here because I've got to actually do this integral. But I'll tell you what. If we pause and look at anything that's a constant, and we don't have to do that quite yet, but if we do, I think you'll be quite amazed. When you start adding these up, what changes here? Well, let's see. Does x change? You know, I'd say, yeah, that one does change, right? Because x is the distance away to the center of that ring. And so as we are adding up different rings in here, the rings are getting further away or closer in. Okay, so x changes. So I'm going to leave the x inside. Okay. But here's kind of the real interesting one. What about this? Does x and r change? Well, they both do change, but don't they change together? Maybe you would notice it a little bit better if I drew a triangle here and said x would be r cosine theta. I call that theta. And r would be little r sine theta. So that when you take an x squared and a y squared, you're going to get an r squared. Of course, I guess you have cosine theta squared plus sine squared theta. But that's just equal to 1. And I guess my point is here that if you look closely at this, these change, but the reason I picked the hemisphere is for you to realize that even though the x changes and even though the r changes, if this is the x and this is the r, the two together is always the radius of that hemisphere. Hence, this right here is really just nothing more than an r cubed. And that means a lot of this stuff is gone. And of course, some of you who put instead of a dq, a dr here aren't going to be able to make that step. You're already saying your R is the thing that is what you're integrating over, and it's not. So that's kind of the first big step here, is to realize that that doesn't change. Now we still got a couple more steps here. This is Coulomb's constant over R cubed, granted. This is X, and maybe now would be a good time to convert my X into an R cosine theta, as we mentioned up here. But the big one is this dq. Let's write the dq as a sigma dA. Now, sigma has been the symbol we've been using for the charge density. Now, I'll just leave it as sigma for a moment. We could obviously pull it out. We could pull the R out there too. But I want to focus now on the dA. The dA then is the charge that is on this surface. Let me redraw my hemisphere, maybe a little bit bigger. But I included a drawing on there so you'd kind of look at that hemisphere and say, okay, as the hemisphere wraps around, there's one of those rings. How do I get the area of that ring? Well, the ring has radius of r, so its area would be 2 pi r times its thickness, which could be a long arc here of ds. I'll leave this other stuff alone for just a moment. I'll take the r and write it as a little r sine theta, and I'll take the ds, and if I label the ds as in terms of an angle back here, this would be r d theta. Perfect. R d theta. And so now I'll pull out what is a constant. R, and R cubed pulls out. Sigma pulls out. Pi pulls out. I guess I could pull out a 2, but I'm not gonna quite yet for reasons that will hopefully be clear in just a second. But there's the R, the sine theta, the pi, the 2, the sigma, and now I got my d theta. And that was the second hint I gave you, that you might need that trig identity. And the r's cancel off. And so you have Coulomb's constant, charge density, times pi. And then we've got an integral from 0 to pi over 2. And so we can think about this angle as a 0 going all the way up to pi over 2. So quite a few steps in there. Not hard mathematics, but every step seems like it's a physics step. What does this mean? 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 And eventually we get to a fairly easy integral to do, which we can then do a u substitution, and we have it. If you want to go one more step, you can put in the charge density by saying that it would be the total charge divided by the total surface area, and you would end up with that. And so there's the final grand finale. And so again, add up a ring. DQ is the big step. And then read it along each way. What does dq mean? Well, it means sigma dA. What does A mean? Well, circumference times the width. What does width mean? Well, length times the angle. Then do the integral. And so each step, look at the integration. All right, well, as I said earlier, for better or worse, put that one behind you. And let's keep working now with our electronics. I would say in chapter 26, we started a group of 3 chapters where we're getting into some practical applications of all of our electric fields. And so we've seen a little bit already. Let's continue. Oh, and that did take a little bit more than an hour, so let me talk a little fast. But I wanted to spend about an hour going through the test, and then at least an hour into this next chapter, chapter 27. It's where we get introduced to Ohm's law. It's why you did the lab last week, Ohm's law. So, let's do this to get us started. As we start chapter 27, let me remind you, you guys with me? Let me remind you of what you have just done. You did a problem like this. We started chapter 26, something like this. The next step is just a continuation of this. Watch, let's review this real quick. If I took a battery, say 5 volts, not a surprise, I happen to have a 5-volt power supply right here. So let me disconnect a couple of things here. Let me move it forward. Let me turn it on. Let me adjust it to 5 volts. All right. So there's 5 volts. All right. Then if I take a capacitor, here's a capacitor, and I were to hook it up like here, then what would happen? What did we learn in this last chapter? Well, we learned that charges, electrons in particular, would come out of the power supply. They would begin to build up. Every time one came out, it would create a little electric field. It would chase another one away. And so we would get some electric field between the plates. We would get some charges on the plate. And this wouldn't keep going forever, right? Eventually, the capacitor would build up to charge and no more flow would take place. Well, I thought we would start today by watching that again. I'll turn off the power supply for just a second. I will take a wire and hook it to my capacitor like so. Now, to visually illustrate what I want you to see, I'm going to put a light bulb in here. So the electrons should come off of here, and I'm going to feed them into the light bulb first. Then from the light bulb into the capacitor. And the point is, if there is a flow going through here, you will see the light bulb on. Doesn't matter, right? Well, one comes in, one comes off. So, yeah, so, okay. Right. So if I turn this on, not a surprise, hey, light goes on. It's pretty bright because they're going on at a pretty significant rate. But again, after a couple of seconds there, it gets dimmer and dimmer and dimmer and dimmer. And so I've installed a little light bulb right here as a visual effect of, say, this is what we've been doing. We know that the charges start to flow on there. They don't take too much time. This happens to be a very large capacitor, so it takes a long time, and you can visually see it. But it's getting dimmer and dimmer. And you guys may not even be able to see it, but up close, I can see that there's just a hair more flowing. In a few more seconds, it will stop altogether. Well, here's our next step. Here's where chapter 27 begins. Let's change it out. Let's change it from a capacitor to something that looks maybe like a long, thin wire. And so I'll represent the rest of my wires as being kind of fat here. And so let me take this capacitor and disconnect it. In fact, I'll disconnect everything so you can kind of see visually again. Here's my 5-volt power supply. I am going to replace it with, oh, let's try this one first. Nope. This one's a good value. With this. Now, I don't know if you can see from your distance, but what I have is a wire wrapped in a coil, very long wire. It's a thin wire. And so the wire actually starts right here on this banana jack here, starts there and wraps around and around and around. And I don't know how long it is. It's something like 10 meters long here, but it wrapped around and around and around, and then the wire is tied up over here. And so this physically is hopefully what you are seeing here. You are seeing that something different is going to happen. What's going to happen is the electrons that come out of here go through here, and they kind of get squeezed, if you will, right there. They kind of get forced into a little tunnel. But nonetheless, they do go in there, and then they continue on, and then they finish their whole path. There is no buildup of charge like we did on the plates. And hence, there is no buildup of an electric field to stop them. So, this whole process just continues. It doesn't stop like it did for the capacitor. I mean, let's give it a try here. So here's my long wire, which we will soon call a resistor. This happens to be kind of a short, fat wire. So in my picture, I am going to connect from here to, and maybe I'll turn it this way so you can see I'm actually plugging it into that wire. So I plugged it into that wire, and then I will go through that 10 meters of wire, if you will, and then I'll go back. And so the electrons are flowing through there. And they're still flowing through there. And I can come back in an hour from now, and they're still flowing through there. And that's the important difference here. That it just keeps flowing. It doesn't build up and then stop. It keeps going. To illustrate it, let me put the light bulb in the circuit here. So I will open it here and feed it through the light bulb to maybe give me a more visual effect. But there is the flow. That's not much of a flow. Let me do something a little, go up to 8 volts, just so we can see it a little bit better. Talk about that in a moment here. But so you can see that I have a flow. And if you watch it for the next few moments up here, you will see that it doesn't change its flow. It just keeps on flowing. Now, if you like analogies, and I think this does help, back here we did something like this. We said, imagine your power supply is this big tank of water. And so that tank of water would be this right here, supplying all these electrons. So unless this thing loses power, that tank's going to stay full. All right. And in this case, what we did is we connected it with a small rubber hose here to a tank. And we said the tank could be a big wide tank or a narrow tank, doesn't matter, but what will happen is the water will flow in, the water level will keep going higher, and eventually the water level will get to the same height as the tank, right? And then the pressures will be equal, and you'll have no more flow. Okay, what's going to happen here? Well, here's my big tank, here's my power supply. What am I doing now? Well, I guess I have a pipe coming out here. But what's a little different here is I've just kind of narrowed the pipe. I could have made it a long narrow pipe or a short narrow pipe. I guess I could even made it a fat pipe, who knows? But I've just opened it up, and what happens to the water? Doesn't it just keep flowing? Does the water ever stop flowing? Well, not as long as there's water in the tank, right? And so is my light bulb flowing? Is my light bulb on? Which means the electrons are flowing, right? And it just keeps going. And so as long as I have this on, it's going to flow. Now I would say that there's probably a question here about the amount of flow. I mean, what would you expect if this little pipe here was really narrow or really long? What would you say about the amount of flow? You would probably say, oh, there's not going to be much flow, right? And I would say the same thing with my electronics here. If I take this long wire and I replace it with a longer wire or a narrow wire, it probably won't have much flow. I don't know if you can see from your distance. I'll pass these around in a second. But this one is much narrower. It almost, probably from your distance, might look like a solid piece, right? Can you see the individual wires wrapped around? This one is a big fat wire. I think from your distance you could even see how fat the wire is. And so if I were to replace this long wire with this one here, which is much thinner, well, that's a little too much, I guess. Can't even see it now. But it is flowing. If I replaced this thin wire with a little fatter wire, let's see, I'll try this one first. I don't know if you can see, but that wire's thinner than this one. This one's a little fatter wire. I would kind of expect a larger flow. And I don't know, can you tell that's brighter than when it was back here? Yeah. And so it's a much easier flow through there. Or this one, better still. This one, I think you can really tell how fat the wires are, even from your distance. So if I connect it to here, you hopefully will see it even brighter and even more flow. In fact, maybe too much. I'm going to burn it out here. I'll turn that off there. Okay. And so this right here, the size of this wire is really determining what is stopping it. This is why we did the lab we did last week, to introduce you to resistance. That's what I'm trying to throw in here, is that what we have here is going to be a resistor. We have a way to control how much flows through this water, or through this pipe. It's like water flowing through here. But it is different than this. But you can hopefully kind of see how we did this first, which then leads to this. I'll change it a little bit.
Why does the light bulb only light up when there's flow?
Why does it only light up when there's flow? Well, the light is given off when it is hot. So like the sun or a match, light is given off when it's hot. It only gets hot when it has energy going to it. And in this case, what happens is the electrons hit the atom. And as they move through, they ricochet off the atoms, making them go faster and faster. So we're using the flow of the electrons, the movement of the electrons, to make heat. Then the heat makes, and unfortunately nature does it the rest for us, but the heat makes the atoms crash so hard that the electrons in the atoms jump up in an orbital, and then when they go back down, they give off light. And all that we don't have to worry about. We just have to get it hot. So you light a match, just get it hot, you got light. Right? Have the sun, get it hot, you got light. So nature does the rest. We just got to get it hot. And now it's not the only way to get off light. In fact, that's a pretty inefficient way, but easy way to get light. Just get something real hot. So light bulbs are like 98% of the energy goes into heat. your old-fashioned incandescent ones. And only about 2% go into light energy. Yeah. But easy to do. Let me go back to, and just kind of, one that seemed to be real nice was this one. So I'll keep this one handy. No, this one here. I'll keep this one handy. I'll pass these around so you can kind of look at them. And I want you to see the different thicknesses in the wire. That was one of the things I was showing you. But I also want you to see one other thing when you get those. Did you see this little connection on top? It slides back and forth. All right, here's why. If I take this and plug it into here, then it goes through this wire. And of course what I did is I plugged it into this side. Fair enough? And it had to go through all 10 meters of this wire. But if I plug it into here, what will happen is it will have to go through the wire to wherever this is making contact, and then go along this bus and out to here. And so if I put my little connector here, it's got to go almost the whole 10 meters. But if I put my connection to there, or to there, or to there, or to there, it goes through much less wiring. And eventually you can see it's bright. And so again, you'll see what I guess I'm trying to do here first is conceptually get the idea of what we're eventually going to call current. Current is these flowing charges. And we can control their flow by how much we stop them, we oppose them, their resistance. Which is actually then the title of today's chapter. The title of chapter 27 is What is Current and What is Resistance? And I'm trying to use those little wires there to give you a feel, and the light bulb a feel, what is current, what is resistance. So I hopefully have answered that in part, that the resistance here is kind of the stopping force. It's saying, look, how much are you opposing this flow? Okay. The current then is really then what I'll say the amount of flow. How many of these electrons really do flow? And so, like I said, I can control this resistance. Very little, and therefore a lot flows, light gets bright. A lot of resistance, very little flows, light gets dim. And I'm going to, like I said, control all of those. Now, if this helps, at least it does to me, is look at this tank of water. This tank of water you'll see many times for these next two chapters. It is a good demonstration of what is flowing. Because water flowing in pipes is a lot like electrons are flowing in wire. You can see water in pipes, so it helps. So what I'm going to do is take this rubber hose, I'll hold it up, I will turn on the pump and say, all right, that pump right there is equivalent to this power supply. This is what is giving the push. These are pushing electrons. This pump is pushing water. As the water flows through the pipe, or as the electrons flow through the wire, they will encounter a resistance. In this case, the resistance can be adjusted by either the length of the wire or the thickness of the wire. I was going to change the thickness, but I already passed those around here. But in this case, if I were to change the thickness of this rubber hose, if I were to grab it right here and pinch it about halfway down, what will you notice? Less flow, right? Is the pump pushing less? No. Why less flow? More resistance, right? Less size to my wire. On the other hand, if I were to unpinch my fingers, I'd get a lot of flow. Not that the pump is pushing any harder, but that there's less resistance. Fair enough? What if I were to turn the pump down and give less voltage to my pump? What do you notice? Less flow. What do you think you would notice if I came over here and I turn my voltage down? Less flow, right? If I turn my voltage up, more flow. If I turn my voltage up, more flow, more flow, more flow, right? And I can control the amount of flow by either controlling the push or controlling the resistance, okay? And that is really the point of the lab here, is what we're going to call Ohm's law. There are two factors controlling the amount of flow, the push and the stoppage.
When you apply resistance to either the pipe or the wire, where is the energy from the pump or the voltage supply going?
Heat. Heat. And so when I touch a light bulb, for example, I know I've been using this one as the resistor, but the truth is this and the light bulb has a very thin filament in it also. The light bulb gets hot, and this one actually is kind of warm to the touch. And so you'll notice that when we do the lab, you'll hook up our resistors and you'll go, hey, it's warm. Hopefully it won't get so warm that it starts smoking on you, but that happens too at times. So we'll try to avoid that. But that's where all the energy goes. All right. And I should say more about that, but I'll hold off on that. But there's certainly more to be added to that. Well, like I said, I just wanted to start here with that basic idea then of you getting a gut feeling of what do we mean by resistance? You getting a gut feeling of what do we mean by the push, the voltage? Because those two result in the current. And in fact, let's put a couple of symbols here on the board here and some units. Resistance is the amount of stopping. So it needs to be measured in some type of units, right? We mentioned this in lab. That's why we did the lab last week, trying to get you started here. What are the units that we use for resistance? Yeah, ohms. And so in honor of Ohm and the work he did and the lab we did and what this chapter is, Ohm's law, we're going to measure it in terms of ohms. How many ohms? So if you look at the ones that are being passed around, you will see some markings on it. This one is stamped, or that's got a sticker right here that says 33 ohms. So between the thickness of this wire and the length of this wire from here to here is 33 ohms. Doesn't surprise me. This one, being a thinner wire, and of course being thinner means we can put more turns on it and fit on the same length, so it's also longer. So it's thinner, it's also longer. Doesn't surprise me that it comes out to be 175 ohms of resistance. I think one of those going around is 11, and the one with the big fat wire is like 2.8 ohms, okay? And so it has how many ohms are in it. Now, the reason I say all that is because in lab we are going to come across some resistors. Try again. Thanks. Yay, okay. And when we come into lab, we're going to have a bunch of resistors. And they look a little bit like this. And so your author has put a little picture here. I'll let that warm up. But I thought I would pass a few around here. Actually, I'll grab one so I can kind of look at it. But these are kind of the miniature version of those giant ones that I'm passing around here. In fact, even these are pretty big. But we like to use big ones because the big ones can handle a lot of heat. So as we often said that, hey, we make our labs idiot-proof. I don't think you can catch these on fire. Please don't try, but I don't think you can no matter how much you try. Whereas the little ones like this or some of the other smaller ones doesn't take much to get them to start smoking and just overdo it with our voltage supply. Yeah.
Is the resistance related to electric flux?
No.
No?
No. So the electric flux, I would say, comes from electric fields. That's part of the push. And so that, if you'll notice, maybe needs to be included up here, but you'll notice missing in the title is voltage. That's what's giving me the push, and it's not included in the title because it's assumed, hey, we've already been talking about voltages. So we're going to continue to talk about voltages, but the push is coming from the voltage. The stopping, I'm glad you asked where it's coming from. We're going to build up to that, but the stopping is coming by really how narrow that little pipe is, how long that pipe is, what the material is made out of, what temperature is it. And so hopefully before today's over, we'll see all 4 reasons why there are resistance. Yeah.
So when a resistor resists something, it produces heat as a byproduct because it's turning the excess energy into heat, right?
Exactly.
So is there something that does not? Is there a type of resistor that does not produce that much heat, or?
No, if it's a resistor, it is slowing the electrons down, impeding them because it's making them hit and make heat.
So they cool down somehow.
Yeah. So they get warm. Now, not overly warm. I mean, you're not that much because they're not usually that much electrons. But here is a picture out of your book, and I think your author's done a good job of saying you should see some of these in the real world. I passed these around. I also have these are ones that you'll see in the lab. And the reason I'm pointing these ones out first is because these actually just say how much is on them. And it just says 59 ohms. All right. But please remember, like the capacitors we did in lab, 59 does not mean exactly 59. Remember those capacitors? I brought those out again. Remember these? Remember we measured them? It said 1 microfarad, but was it really 1 microfarad? No, it was kind of close, right? Same thing with our resistors. It'll say 59, it'll say 75, it'll say 30, but the truth is it's only somewhat close. In fact, some of these resistors get so small, and again, we tend to use big ones, so I wouldn't be surprised if most of the ones you see in lab look like this and they actually have a number stamped on it. Even if they have a number stamped on it, we're going to hook it up and measure it because remember, it's only close to 59, not exactly 59. But it's worth pointing out the color code, right? And so I don't know if you noticed, particularly the ones I'm passing around or the ones in there, they can get so small that if you put a number on them, you can't read them anyways. So instead, you color code them. And so here is one that is color code. You can see a red, a black, and a brown band, 3 bands, and in this case actually a 4th band. Same thing over here. Well, all of these, you can see the 3 bands and the 4th band. I grabbed this one out. This one happens to be a blue, a red, and then a silver. And so those mean something. And so your author points out that each color in the rainbow has an assigned number to it. Table 1, I believe, in your book shows this and says, here is the color code. Now, to be quite honest with you, I'm not going to have you memorize the color code. Don't even mess with it unless you continue on in your education into your circuits and your other classes. In fact, maybe I should ask, do you guys have to memorize it in your circuits class? No, you can look up. You can have a chart. Okay. So if you have a chart or if you memorize it, great. This class, like I said, I'm just taking this as a moment to point it out. Because the truth is, here's what we'll do in this class. You want to know the resistance of this resistor? Grab a meter, hook it up, and you got it. And that's really what we're going to do. But you will notice that they all have these color codes on them. And so your author takes a moment, and I should too, especially for those of you in the circuits or those who will go on and do more circuitry stuff, that most of them do have a color band on here. So it's interesting how it works. The first color, which in this case is blue, if I scan across, it says blue. It says it's a 6. The next one is a red. So as I scan across, red is a 2. And my third color is a red. And here's where it gets kind of weird. You don't want the number 2. The third band is a multiplier. And so it means 10 to the 2. So times 10 to the 2. All right. So the first 2 bands give you digits. The next one gives you the power that it is raised to. So in this case, it is 6,200 ohms is what this would say. If I turn on my meter, I hope I will get something within a few percentage of that, or actually this one has a silver band at the end, and so this says it should be accurate to within 10%. And so the fourth band is telling you what is it accurate to. So that's why some have no color, because they're saying that they're only 20%. So they're just quickly mass produced. They cost about a penny each, and say, hey, 6,200 close. Fortunately, in most of our electronics, close is actually good enough for it to work right here. Agreed. And so I don't think it's hard to memorize, but I'm just saying I'm not going to have you memorize it. If you want to memorize it, fine, and if you go into electronics, you probably should. But there it is. So 6,200, looks like I'm closer to 6,300 than 6,200. So whatever the percent difference is, but there's my resistance.
So when you held it like that, how come it didn't want to go through you?
Oh, you know it does, and I should be careful. Because it could go through me, and that would have an effect. Although that should lower the resistance, and I got a reading too high, so I should probably be a little bit better. And then same thing, I should get a good clamp on there, right? I don't want to get any extra resistance that is from my wires versus my resistor, because of course this is going to measure the resistance all the way through. And didn't I have like 63.3? Well, here, I'll just touch it. Does it change? Yeah, see, so the parallel path through me is picking up in that last decimal. Yeah, so it is picking up. So yeah, I to get a more accurate reading, I shouldn't touch it. I should keep it away. And I know, and then you're going to say, what about the air? But that's less than me, and I gotta have the air in there. I guess we can make the air drier. Okay. Well, like I said, there is that first idea, the resistance. Let's get over to here. The second idea is the current. The current is this amount of flow. And so I think you're starting to get a good feel for what do we mean by the resistance. The amount of flow is what we call current. And so let me put that here. Current. What is current? Well, let's try to get a better picture in our mind of current. The traditional symbol, as we mentioned in lab, is I. Oh, and I guess I should have done that back here. The traditional symbol for resistance is R, measured in ohms. So the traditional symbol for current is an I. It's measured in units of... Okay, and for those of you who remember from the lab, or maybe from some other class, it is measured in amps. And again, in honor of Ampere and the work he did. What is 1 amp? What is the definition of 1 amp? Anybody know? It is a bunch of electrons. How many? Does anybody remember from lab? No? I told you 6. I didn't do the 6.2, but I'll do the 6.2. 6.2 billion electrons every second is going to represent our current of 1 amp. And the reason I wanted to emphasize that is I think that as we go forward with our electronics, we start labeling current as amps, current as amps, current as amps. And it's so easy to forget that current is really billions of electrons flowing. And that's what I want to make sure I emphasize before we go further and kind of blow that under the rug.
Why 6.2?
Oh, why the good question. Why the 6.2? Well, how many electrons does it take to make 1 coulomb of charge? 6.2 billion. So this is 1 coulomb of charge every second. That's why the choice. Remember, 1 electron has 1.602 times 10 to the minus 19 coulombs in it. If you take the reciprocal of that, right, this is coulombs per electron. The reciprocal of that is how many electrons per coulomb? 6.2 billion electrons. Okay? And so these electrons are really small. And so that's why, again, we're going to measure them not in how many electrons. Because if you did how many electrons, we would be up here going, okay, how many electrons are flowing? Oh, 3 billion. Just a lot easier to say half an amp, right? And don't we do the same thing with water? If I came over here and turned this on and said, how much water is flowing? You probably wouldn't tell me 3 billion water molecules. You would tell me something like 100 milliliters a second, right? You would use milliliters or liters. You would put all of those water molecules together in a big group. You wouldn't tell me how many water molecules, fair enough? And that's exactly the same idea here. We're not going to say how many electrons, we're going to say how many amps, where 6 billion represents 1 amp. And like I said, it's a good way, I think, to get started with our circuitry here, is to keep that mental picture of what really is current. Current is this flowing charge. In fact, it's why your author starts off with the very first figure in the book and says this, or the chapter. He says, let's take a close look at what do we mean by current. Now, let's put some equation in here. He said, because the concept of the current is that it is the flowing charge. The symbol, of course, is I. The units are, of course, amps. But the picture he wants you to have is this. And maybe he should do a better job and conclude the wire here. But he has something that looks like this. Here's, say, the wire. Maybe here is the battery. But kind of like I've been doing for this first half hour here is saying, look, I take my battery, I run those electrons through here. If I could look on a microscopic level and draw some cross-sectional area A, then there would be charges moving through there. And so that movement of charge is what he's showing in that picture. And that's what we mean by current. Current, then, is the rate at which the charges flow through that little area. And that's where we want to get started with our math, is to say, let's turn this into an equation. What is current? Current is the flow. Now, maybe this isn't such a good picture, because this one is showing positives moving. What's really moving in our wire? Right, and so this is that basic idea in concept, but in practice it may look a little more complicated. Let's look at other options. You see, I would say we really are looking at this in our wire. Figure D here says that in this wire, what I really have is electrons are moving this way. So even though that first picture looked something like this, where positives are flowing, what I really have is negatives flowing. And that's probably a better picture of what's going on. But keep in mind, there's many possibilities. For example, what if I had a chemical solution, like in a battery? Let's just take your car battery. It's got the sulfuric acid and the lead. It's got a bunch of positive and negative ions flowing around. Isn't this what happens inside the battery? So even though this may be a more accurate picture of what is happening in a metal wire, it doesn't tell us the whole story, because we could have both positives and negatives. We could have situations that we only have positives.
Is it positive charges don't move?
Positive charges don't move in a metal. Why not?
They're protons.
They're protons. Where are the protons? In the nucleus, right? The nucleus and the metal is a solid. What do we mean by solids? The bonds are permanent. They can't move. Exactly. So this is why we have a picture in metals. But what would happen in a liquid? What if this was sodium chloride? You would have a positive sodium floating around. It would move. It can move. It's in a solution. You can have chlorine. It can move. Okay? And so we can have each of these four situations. So please keep in mind that our picture for a wire is really just negatives are flowing. But a broader spectrum of this is we could have situations where you have positives and negatives. Now I must admit, this is what we are going to do probably 99% of the time. Wires. And so which ones actually move? The negatives. But here is an extremely important concept that you get a hold of. Look carefully at this definition. The definition says the current is the direction of the change of charge. So, let me draw a couple scenarios up here. Why don't I start with what I might call the more realistic situation, the one that we're going to do 99% of the time. If I were to take a wire, and for the sake of conversation, let's say that there is 100 electrons over here. So I'll call that negative 100. Okay? And again, for the sake of conversation, let's just say there's negative 50 electrons over there. Compare that with me to say, let's say that I have 100, and I'll put electrons here. Electrons, electrons. Let's say that I have 100 sodium atoms on this side and 50 sodium atoms on that side. Now, when a sodium atom goes from here to there, doesn't this become 49? And this becomes 101? Right? And so the change is that way? Right? This one increased, this one decreased. Ah, careful with your math. What if an electron went that direction? What's the charge here? What's the charge here? What direction is the change? That way. Okay. So, notice that in both scenarios, Whether a positive moved or a negative moved, this side increased. This side decreased, right? Here's the tough thing to keep in mind. It drives students crazy all semester long, but I hope you figure it out real early. The direction of the current is not defined as the direction the particles are moving. Did you catch that? I'll put it this way. It does not equal dx dt. The current is not defined by the direction the particles are moving. It's defined how? The direction of the change. So if you have a positive that goes from left to right, then the current is left to right. If you have a negative that goes right to left, which way is the current? Left to right. And so the current is in the opposite direction that the negatives actually move. And that's easy to miss. And so when we have a situation like B, and somebody asks you what direction is the current and what direction are the particles moving, it's moving from the right to the left. Fair enough? That's the easy one. But did you catch this one? What direction are the particles moving? Left to right. What direction is the current? Right to left. You catching that? I'll say it again because it's easy to miss this. The direction of the current is not necessarily the direction of the flow of the particles. That's not what we're going to be interested. What you will see real soon is we are interested in energy. The energy comes from the charges. We are interested in the change of the charges. Whether they are positive or negative doesn't really care to us. What direction they are moving doesn't really matter to us. We care about the energy change, and that has to do with the charge change. And so as we go forward, please keep in mind that the current can be thought of as the direction positives are going. Even if we have negatives going that way, the current is this way. Which is why when you have something like this, and you've got half of the positives going one way and half of the negatives going the other way, does that mean we have no current? Do those balance each other? No, because that's not the definition of current. What's the definition of current? The change in charge. So when I look at these three, those three give me a current that way. When I look at the -2 going that way, what does that give me? A current that way. All 5 of these particles give me a current that way. They don't cancel each other. And that's what we want to know, because if any charged particle is moving, they will contribute energy to our system. That's what we're going to care about. It's too bad that some go left and some go right. It would be nice if we only had just one set of charges. And then we could have just easily said, the current is in the direction that those move. In fact, I would argue that I wish that the electron had been labeled positive, so at least the beginning student would understand that the direction of the current and the direction of the flow is the same, but unfortunately it's not. The electrons are negative, they're the ones that move in the wire, and as a consequence of that, we have pictures that look like this. Which way do the electrons move? From negative to positive. Which way is the current? And so we will label the current as going from positive to negative. Even if we have a scenario where we have no positive flowing. So now you can see the dilemma that because you have positive and negative, you cannot just pick the direction of flow to be the current. Some go put one way, some go the other. You have to have the two. Well, bummer. Out of time. Wanted to show you a little bit more before the lab tomorrow, but we'll make do. And I'll see you on Thursday, or lab tomorrow.